Applied sequence and transform models for text. Natural language processing language models. In this video, we'll cover language models, an overview, vectorization of characters, and sequence preprocessing. Let's get started. Language models. A statistical language model is a probability distribution over sequences of words. Given such a sequence, say of length m, it assigns a probability distribution to the whole sequence. As the number of words coming before a word varies depending on its location in the input document, the distribution is usually conditioned on a window of n previous words rather than all previous words. This equation is especially useful for translation systems and speech systems, as it is used to determine whether a word sequence is an accurate translation of an input sentence. In existing language translation systems, for each phrase or sentence translation, the software generates a number of alternative word sequences. For example, I have, I had, I has, me have, and me had, and scores them to identify the most likely translation sequence. In machine translation, the model chooses the best word ordering for an input phrase by choosing the most probable based on a language model, scoring each output. Data sparsity is a major problem in building language models. As we will see, and most possible word sequences are not observed in training. One solution is to make the assumption that the probability of a word only depends on the previous n words. This is known as the n-gram model or unigram model when n is 1. The unigram model is also known as the bag of words model, and we saw how to compute n-grams in Keras in the second video of this section. Estimating the relative likelihood of different phrases is useful in many natural language processing applications, especially those that generate text as an output. Language modeling is used in speech recognition, machine translation, part-of-speech tagging, parsing, optical character recognition, handwriting recognition, information retrieval, and other applications. So as we saw in the second video, n-gram language models. In n-gram language model, the probability distribution of observing the sentence is approximated as follows. It is assumed that the probability of observing the ith word in the context history of the preceding words can be approximated by the probability of observing it in the shortened context history of the preceding n words, and this is known as the nth order Markup property. The conditional probability can be calculated for an n-gram model frequency counts, and the terms bigram and trigram models denote n-gram models with n equals 2 and n equals 3 respectively. Typically, an n-gram model probabilities are not derived directly from the frequency counts because models derived this way have severe problems when confronted with any n-grams that have not been explicitly seen before. Instead, some form of smoothing is necessary, assigning some of the total probability mass to unseen words or n-grams. Various methods are used, from simple add-1 smoothing, which assigns a count to 1 to unseen n-grams, unformative prior, to more sophisticated models such as good, Turing, discounted, or backup models. N-gram language models have two main issues though. That is that the models are very sparse, and a word sequence under evaluation may never appear in our corpus. And also we have storage issues, as we need to store all the n-grams that we saw in our corpus, which increases as n increases. So we can solve this with neural network language models. So neural language models or continuous space language models use continuous representations or embeddings of words to make their predictions. Continuous space embeddings help alleviate the curse of dimensionality in language modeling, as we saw in the first video with word embeddings. Specifically, as language models are trained on larger and larger tasks, and the number of unique words, the vocabulary increases. The number of possible sequences of words increases exponentially with the size of the vocabulary, causing a data sparsity problem because of the exponentially many sequences. Thus, statistics are needed to properly estimate probabilities. Neural networks avoid this problem by representing words in a distributed way as nonlinear combinations of weights in a neural net. An alternative description is that a neural net approximates the language function. The neural net architecture might be feed-forward or recurrent, while the former is simpler and the latter is more common. Typically, a neural net language models are constructed and trained as probabilistic classifiers that learn to predict probability distribution. And that is, the network is trained to predict the probability distribution over the vocabulary, given some linguistic context. This is done using the standard neural net training algorithms such as stochastic gradient descent with backpropagation. The context might be a fixed size window of previous words, so that the network predicts from a feature vector representing the previous k words. Another option is to use future words as well as past words as features, so that the estimated probability is the following. This is called bag of words model, and when the feature vectors for the words in the context are combined by a continuous operation, this model is referred to as a continuous bag of words architecture. A third option that trains slower than the continuous bag of words but performs slightly better is to invert the previous problem to make the neural network learn the context of a given word. More formally, given a sequence of training words, one maximizes the average log probability, where k is the size of the training context and can be a function of the center word. This is called a skip-gram language model, and bag of words and skip-gram models are the basis of the word-to-vec word embedding, which we saw in the first video of this section. Instead of using neural net language models to produce actual probabilities, it is common to instead use the distributed representation encoding in the network's hidden layers as representations of words. Each word is then mapped to an n-dimensional real vector called the word embedding, where n is the size of a layer just before the output layer. The representations in Scikit-Learn models have distinct characteristic that they model semantic relations between words as linear combinations, capturing a form of composability. For example, in some such models, if v is the function that maps a word to its n-dimensional vector representation, then as we saw in the first video, if we did the vector of representation of a king minus male plus female is approximately queen. So let's look at language models in Keras using a recurrent character model. Let's train a language model where a character-based recurrent neural network and sample from it to generate text that is similar from the corpus that we trained it on. Here, let's choose the corpus of Shakespeare's writing. Given a sequence of characters from this data, Shakespeare, we can train a model to predict the next character in the sequence. Longer sequences of text can be generated by calling the model repeatedly. The following is an example of the sample output when the model is trained in the tutorial for 30 epochs, starting with Q. So in this case, we input Q, then actually outputs the rest. So in this case, we can see it's reasonable good Shakespearean-like text, which has been generated. While some of the sentences are grammatical, most do not make sense. The model has not learned the meaning of words, but consider the model is character-based. That is, when training started, the model did not know how to spell an English word or that the words were even a unit of text. The structure of the output resembles a play blocks of text, generally beginning with a speaker name and in all capital letters similar to the dataset. As demonstrated below, the model is trained on small batches of text, 100 characters each, and is still able to generate a longer sequence of text with coherent structure. Now we can download and process the dataset from the following URL, and we can look into the text, and then the length of text that is the number of characters in it, and the unique characters within the file. We can also take a peek at the first 250 characters in the text example. So we know we have about 1.1 million characters here, and we have 65 unique characters, and this is just a peek to the dataset that we have. Let's process the text. So first we'll vectorize the text. Before training, we need to map the strings to numerical representation, so we can create lookup tables, one mapping characters to numbers, and another from numbers to characters. And we can do this by creating a mapping from the unique characters to indices, as follows. Now we have an integer representation for each character. Notice that we map the characters as indexes from 0 to the length of the unique characters that we have in the coding. So we can see a map here, where we map the new line separated to encoding 0, and then 3 maybe to 9, or a letter A capitalized 13. And we can show the first 13 characters from the text that are mapped to integers. So in this case, as follows. So the neural network will see this and will predict integer representation, which we can then encode back into our text format. The prediction task. Given a character or a sequence of characters, what is most probable next character? This is a task we're training the model to perform. The input of the model will be a sequence of characters, and we can train the model to predict the output, the following character each time step. Since recurrent neural networks maintain an internal state that depends on previously seen elements, given all characters computed until this moment, we can then model what is the next character. So we can create training examples and targets. We can next divide the text into example sequences. Each input sequence will contain sequence length characters from the text. For each input sequence, the corresponding targets contain the same length of text, except shifted one character to the right. So to break the text into chunks of sequence length plus 1, for example, sequence length is 4 and a text is hello, the input sequences would be hell, and then the target sequence would be lo. To do this, we can use first the TensorFlow dataset from TensorFlow slices function to convert the text vector into stream of character indices. The maximum length sentence we want for a single input and character, and we can also create the training and targets using the dataset from tensors. We can have a look at the first 5 examples here, and the batch method lets us easily convert these individual characters sequences of the desired size, as follows. And we can look at a few samples here. Now for each sequence, we can duplicate and shift it from the input and target text by using the map method to apply a simple function to each batch, where we have the sequences.map, and we can print the first examples of the input and target values. So in this case, the input would be this string of character sequences, and the output we're trying to predict is shifted one character along. So we're trying to predict, actually in this case, this space character here after this U. So each index of these vectors are processed as one time step. For the input at timestamp 0, the model receives the index for f and tries to predict the next index for I as the next character at the next timestamp. It does the same thing, but recurrent neural network considers the previous step context in addition to the current step input character. So we can have a look at that here as well. We have step 0, input of f, and then we export the output to be I. In this case, this is the integer representation of 18 and 47. Similarly, as we go down, it would be similar here. So creating training branches. So we use the TF data to split the data into manageable sequences. Before feeding this data into the model, we need to shuffle the data and pack it into batches. And we actually do this using the dataset.shuffle, specifying a buffer size, and then batch them. So the buffer size to the shuffle dataset is designed to work with possibly infinite data sequences in the TF data object. So it doesn't attempt to shuffle the entire sequence in memory, so instead it maintains a buffer from which it shuffles elements, and we have to specify this here. In summary, we've covered language models, an overview, vectorizing characters, and sequence preprocessing.